All right, I think this is the source of audio that doesn't have the humming in the background. I think, yeah, this one has the fan noise. Oh yeah. All right, so away we go. I'm sorry for the inconvenience today, but there may be some advantage to doing things this way. Give me a second here. So, as a recap, we started with this concept of a position out here. And as we move along, we change position, and basically there's a delta S, no big deal. So then you look at delta S over delta T, then you say that's an average. You move it down by taking a limit over it, and you get the relationships that you've seen in physics too. Now, he talks about the difference between speed and average speed. He talks about distance traveled, for example, the average velocity of something that starts in position 0, moves 10 foot and comes back to 0. That can be looked at a little bit different. The instantaneous velocity is basically at a certain time t. You look at the speed at that t. If you look at the average, that could be the distance covered over the time it took. In this particular case, distance at total traveled was 0. So that's something to think about and is embedded in these problems. Same thing could be said about average acceleration, and again goes in and takes the limit, and you get the secondary relationship, or primary, depending on the way you look at it. The second derivative of the position with respect to time is the acceleration. This was the oddball. The reason it was oddball is your perspective. In essence, in the case like this, where you knew position as a function of time, in other words, this, it's pretty easy, or may I restate that and say velocity as a function of time. It's pretty easy to do this. However, if you don't have velocity as a function of time, but you have velocity as a function of position, then you've got this problem. And the problem comes back to, this is the definition, but it can be rewritten like this. If you look back, this is nothing more than velocity. So what you get is the acceleration is equal to, well, usually it's written this way, v dv ds. Now, what generally happens after that is they take the ds over to the other side, and you'll see acceleration ds with this moved over here equals to v dv. So this is an interesting relationship in which you have velocity as a function of position instead of velocity as a function of time. We talked about that in class and gave a particular case, and I'll go ahead and fill that in for people who were not there. And that is, let's say you had water flowing through a pipe. Large diameter back here. Oops. Here. large diameter back here. The pipe is flowing. Maybe it's flowing at 10 feet per second. But when it reaches the small diameter, it has to go faster. So let's say the velocity up here is equal to 25 feet per second. Now, if you stare at a velocity at, say, this point, you say velocity there, it's got to be between 10 and 25, so let's just say it's 15 feet per second. You stare at it over and over, and it stays the same, i.e., it is not varied with respect to time. But you might conclude by staring at it and saying, oh, velocity does not vary with respect to time, so therefore the acceleration is equal to 0. You would be wrong in that assumption. Here's why. You are staring at this. As you stared at it, you look to the left of it, say a particle here and a particle there. So another person's staring here to the left of it, where this is, say, a delta S. Somebody's staring to the right of it, and just say in case that you have something like that. Say it's 15 here, then say it's 16 here, and then say it's 14 here. Now, if you stare at this particle, if you track it, you set on it, and you were glued to that particle, you would see it would be 14, then 15, then 16. Then, in fact, that particle does experience an acceleration equals to some sort of number. It does change its velocity with respect to time. You've decided to stare at this thing, but what have you done? Okay, so if you look at this, if you go back to that equation, you would see the equation that's sat right here. This, let's go back over here. Acceleration is equal to V, change in V with respect to S. You would look back before you at certain delta S, so you would, to get an approximation, you might do something like this. And say this delta S was equal to 0.1, for example. Let's just say that's the distance. Okay, so the velocity you would see would be 15. Change in velocity would be 1, and the delta S would be 0.1, and it would see about 150 units of length over units of time squared. So if I want to claim, and I guess I did claim that it was feet per second, so it would be feet per second squared. So in fact, there is acceleration. So now let's go on from here. I covered this. So essentially it was basically if you had constant acceleration, then you can pull this out of the integral and you'll get a term that sits like this. Then you could say, okay, this is for constant acceleration. Why is constant acceleration so important? Well, gravity is equal to a constant. The other thing is if you have say a thing on the floor, a box you're trying to move, and you push on it with a certain force, if the force is constant, then unless you're shedding mass like a rocket would, then the acceleration will be constant. By placing a constant force on something, you're going to get a constant acceleration unless the mass is changing. The reason that is pretty simple. F is equal to ma. If this is constant and this is constant, then this is going to be constant. So that's why this one's particularly important. In addition, there's a whole set of problems that relate to parabolic motion. For example, throwing a football, shooting a cannon. Those will come up shortly. So we go through this. We take this velocity, and what do we do with it? We stick it right in here. Now, we pull it out, but we now have a t in here, which tied to the acceleration, so you can see a t squared. The velocity would come up with this. The integration constant, you could say, would come out of here. One of the things that I talked about in class that I'm going to say real straight here is this should actually be written like so. and this should be at 0. So this is not generally written this way up here, but they have a symbol down here. The S0 implies that that 0 is attached to it. So just be aware of that. Okay, once you do this, you get the S0 over here because you get S evaluated from S0 to S. You take the S because on the left side you're going to get S minus S0. You take the plus S0, move it to the right, and you got that. Okay. What do you do next? Well, there's not much you do next. Okay, so because you're done. You've got velocity and position as a function of time, acceleration being constant. However, if you have a situation in which you have this, then the acceleration ends up being pulled out. This ends up being pulled out, but you end up with v squared over 2 evaluated from v and v0 on the left, which is why you get this, which is how you get this 2 that gets put up against this. Now, what's interesting about this is that, and I'll just mention it right now, later on you'll see 1/2 mv squared, and obviously there's some sort of relationship or corollary between these two. And in fact, without being too leading, they can be directly related. So here is the two, or here's the relationship. Okay, then he has a whole set of problems which I'm going to come back to and start working some of these, but I'm going to go on and run through the next section of erratic motion, which starts about right here. It's really only 2 sections, or actually 3, but I consider it 2. Okay, so in this, you're back to the same concept, the relationship. If you look at erratic motion, you see something very interesting here. Here, I'll just use the bottom of this page. So, erratic motion. Okay, so if you look at erratic motion, you basically have S, then you have ds, dt will get you v. So let's move this to the right. You'll get v, and you'll get acceleration equals to dv dt. Now, okay, so if I look at this side, let's stare at it this way. In this way, I'm moving down the chain. So in other words, if someone told me what s of t, and let's just make something up, t squared, I have something like that. I'd take a derivative, I get a velocity. Okay, so if you wanted to do this, have at it. Okay, so then I got a velocity. I go down one more step, and I get that. But what I did is I started here, and then moved that way. So I took a differential to move this way. If in fact, though, I have acceleration, I have to move the other way. So if I have acceleration being equals to, say, 4, now, this is given the fact that maybe it's something besides 4. So maybe it's 4t squared. So it's not constant now. What do I do to get move back up the chain? I have to use this relationship, and I have to do this, and then let me get rid of this and move that arrow over. And I'll just put a box around this. So then what do I do? Well, I have to use this relationship for the next step, which basically says so in this case I was given this, in this case I was given this. This case I move down, this case I move up. If I'm going up, I take integration. Okay, so let's take a case that sits across the entire spectrum here. Oh, sorry, t. and velocity. And we'll just say the velocity starts out at 0, says moves up here to say 10, and just to make it easy for myself, it took 10 seconds, moved across to here, and there may be some velocity outside to the right of it, but we don't care. We don't care anymore. So, and let's say this is 20 seconds. So the question may be posed, what's the acceleration at, okay, so here. What's the acceleration here? What's the acceleration here? What's the position here? So in other words, I could be looking for the acceleration or the position. I could be looking for the acceleration or the position, and we might as well go out to 20, and we can look for the acceleration and position. We're caught in the middle. We're caught right here. So to move to position, again, I'm caught right here. To move to position, I got to take an integral. To move to the acceleration, I take a derivative. So I cannot do that, and I cannot do this. So again, the direction goes this way, direction goes this way. So what do? Pretty simple. Acceleration is equal to the slope, not the stope, but the slope. And so the rise over run the slope of that line, it rose 10, and it took 10 to do it. So, so the acceleration is just going to be equal to 1. And it's going to be equal to 1 all the way out here. So now you have to put a time position on this. So time here. Now, acceleration, let's say that's 15 seconds. Acceleration at 15. Going to be equal to, well, that's a flat line, so it's just 0. Now, there's always a discussion and about the point that sits right there. And I'll put it in an interesting context. You go to right here, and you change your velocity instantly. That's not good, because if you change your velocity instantly, you change from an acceleration of 1 to an acceleration of 0. There is a term in here that is not talked about in this book, and it's called the jerk. And it's basically the change in acceleration. Why is that important? Because F is equal to ma. And if I wanted to know the instantaneous change of a force over time where the mass wasn't changed, I would basically be looking at that. So if you have a quick change of a force, say you went from 10 pounds to 0 pounds instantly, or you went from, say, the reverse, 0 to 10, you're going to basically chip away at the instrument or whatever it is you're doing. So this is a concept that you can get into when you're looking at dynamics, that this is an erosive concept to mechanical equipment. However, if you go into MATLAB and you put these two functions together, and then you look at what the change in velocity with respect to time right at 10 seconds, t is equal to 10, believe it or not, it comes up with a half. So it will take this and average it. That's, I will try not to ask that question, because that's a nebulous question. It could be anywhere between 0 and 1, but MATLAB is built around circuit theory a little bit more, so it will pick a half. Now let's look at the position. Well, if I'm looking for a position and I have the velocity as a function of time, what do? I do this. Why? Because ds dt is equal to velocity. So with that concept, take the t over, put right here, you get this term, leave the ds over here. And so now you're looking at something a little interesting you got to pay attention to. Let me rewrite it up here, because I'm going to try to accentuate something that needs to be paid attention to. T0, S at T0, T, S at t. Notice these go the same way. Why is that important? Technically, because you have two regions here. You have the region that sits right here, and then you have the region that sits right here. Okay, so if you look at it, really the right-hand side simply states what's the area under the curve. That's all it's stating. So if you look at this part, and I say I'm only interested in this area, and said that was 5 seconds, this will be 5. So that area there will be 5 times 5, and you're missing the upper part, so you get half of that. So you get 12.5. Okay, but the question is, look at the left side real close. What did you do? You basically went from position 0, s at t equals 0, was or is going to be specified as 0, and you're going to the s at 5 seconds. Oops, ds. So basically, the s at 5 minus the s at 0 is equal to 12.5. Now, you put down the ruler, and it went to 12.5 after 5 seconds. Now, I didn't ask this question, but let's ask this question. What's the position at 10? Now, you have two choices here. You can do this. You can start from zero, s at 0, and then velocity, time, and s at the time. Well, this will be 10 seconds, but I'll put that in a second. But the key was you started here. Okay, you can start and figure out the area here. So here's what I'm saying. Let me see if I can be a little bit more precise. Look at the triangle. This was 12.5. Okay, so if I integrate from here to here, I have to include the area, which is 12.5, in addition to the area after this, or this area right here. So, what is the area total? It's essentially 12.5 plus this area. Well, that's more complicated than saying, okay, this is 10, and this is 10. So the total area there, integration from 0 to 10 seconds of the velocity, which is a linear function, which is just t. This integral will be basically t squared over 2, evaluated from 0 to 10, which ends up being 10 times 10 divided by 2. Guess what? It's the same thing that you would get if you were looking at the area of the total triangle. If you're looking at the area of this triangle, you just say it's this times this divided by 2. So that's fine. You've got it. The next thing is, if you want to make it difficult for yourself, you can say, I'm going to integrate from 5 to 10. So I'm going from here to here. Well, but if you're doing that, the left-hand side, now pay attention to this, the left-hand side has to have the position at 5 seconds. And this will be s at 10. Okay, I already know that that's 12.5. So let's take a look at this. So s at 10 minus 12.5 is equal to, take the integral, oops, I didn't put down the integral, t squared over 2, evaluate 10, 5. Now, if I take this, t squared, what am I doing? 10 squared over 2 minus 5 squared over 2. Now, what happened here? This is 25 divided by 2, 12.5. So this number and this number cancel out. You get back the S at 10 is equal to, I never figured that out. That's 100 divided by 2, or 50. So my point here is be careful when he writes this in the text that you have an understanding that, and he may not do a good job of that, but he might. I don't know. He just makes it kind of generic. But essentially, that's the one thing to look out for, is that this lower limit over here is directly connected to the lower limit here. The upper limit here is directly connected to the upper limit here. As long as you keep that in mind, you're good. Okay, so what's the velocity at 15? How far did this thing go in 15 seconds? Well, here, the beauty of this type of lecturing is this. I'll just move it out of the way, get back close to it, and what you'll see is if I wanted to, I can find the area of that. Okay, so if I find the area of that, what is it? It's 100 plus the area of that. The area of that is, I move over 5, and I'm at a height of 10. I'm sorry, I said 100. This area right here is 50. I said 100, wrote 10, should have said 50 and wrote 50. Now, this area right here is 50 as well, so I've gone 100. So my change in S from time 0 to time 15 seconds is 100. Now, what do I do if I want to go to 20? Well, I just add in the area right here. And what is that? That's another 50. I move 5 at a height of 10. And I get equals to 150. So I moved 150. So that's erratic motion. Erratic motion is finding the slopes of a drawing or the area under the curve. Let's look at the problems he might have. Well, they all look the same. They basically give you a drawing. And in this particular case, if I'm going to S to V to acceleration, because he gives me S, then I have to get V, I have to take, let's see if I can write on this. Seems to do okay. I basically have that. So essentially take the slope of things. If I go one more step, take the slope again. And so he's done so in actual form. He's given you the equation. And then basically based upon this information, he drew the next plot in its two regions. Then you go down and you do this again. So what do? If you look at it, the slope remains constant from here to here, and it also remains constant from here to here. So look at the slope of that line. It just becomes 2. Slope of that line becomes 0. So let's, when I close this, it'll erase those. Okay, so here I'm looking at acceleration. Okay, what do you do to do acceleration? You go from acceleration to velocity to position. Now I've written these backwards. Let me do this. Let me redo this. If I list them this way, in my chart I had them listed this way. So if I have acceleration, I'm going backwards. I have to, before I was taking the differential, right? So this time I have to take the integral. So in other words, A dv dt, move the dt over, and I'll have acceleration dt and dv. So if I want to get if I'm given the acceleration and I need to get the velocity out of it, I've got to integrate, and I've got to integrate again. It's that simple. So let's see how he does it. Fairly simple case in which it's constant, constant. Well, that's kind of nice because the next plot should have straight lines. Okay, so you take area 1. What you could do with this, let me shrink it down. What you could do, you could, since you know it's constant, you know it's going to be linear. So in other words, if A is a constant, V will equal linear function, and position will equal a quadratic. That's just the way things go with integration. So, so what you could do is you could find the distance, the velocity or the integral here to get this point right here, and then draw a straight line because you knew it's linear. And then get yourself out here, find out what this is. Now here's the difference. Okay, you got to be really careful here. Okay, so you relate this to this. Let's look at area 2. Area 2, he's going to T whatever. He's wanting to know the T it needed to stop the car. So what is he doing? He said, I'm bringing it to 0. That means this area has to be equal to that area. Meaning, okay, now let me rephrase that, because this is a negative area and this is a positive area. They have to add together such that they become 0 at this point. Now, in an integration sense, now in a physical sense, there's no such thing as a negative area, but in an integration sense, yes, there definitely is. It's below the axis. So what you do is you basically figure out how far you need to go. Well, if this is 2 and this is 10 and that's 10, that's 100. So if I'm going to go down here and say, how far do I need to go here so that this area is offsetted at 100, then I'm going to say delta t, not t, times 2, it's got to equal to 100. That gives me the delta t is about equal to 50. Okay, and so if it's 50 seconds to make this area cancel that area, and it was 10 seconds before, you see the 60 seconds. So in fact, this area offset that area, and you're good. Now the key is you got to figure out, once you figured out how far it went, you can work yourself out to the point where you can find this. Now you know the minus t comes from right here, but the 120 is the part that you are looking to figure out. Now, once you have this curve, and I'm hoping or assuming he'll go to the next spot, and that is, and he does. Okay, so here's the difficulty here. It's not as easy to draw quadratics as it is to draw linear straight lines. So now you've got to pay real close attention here. And so sometimes in this step, it's best to go back to the set of equations and work out of here, because you'll get the actual term. Now, you could do this another way, as you know, and I'm almost hesitant to come up with this, a plus bt plus ct squared, and you know that's what you got to end up with if your acceleration is constant. And you could work yourself back from here, but it's better to go the way he's done and take the actual term and put it right in here. And again, tying yourself from this and this being tied together, and the s and the t being tied together, and you'll end up going through to the point where this part's pretty easy, and you'll get that. Now, the difficulty comes in here. Now, you know between 10 and 60, which is between this spot and this spot, that you have a velocity that sits here like so. So, in fact, and maybe I'll zoom in on this a little bit. In fact, you knew, or you were supposed to have known, or maybe you found out, that this thing moved 500 meters in its well, you can find that out. Okay, let me put it to you this way. After 10 seconds, you can find this out right here. You found out the thing moved to 500 meters. Or at 10 seconds, it had moved along 500 meters. Notice the connection here. In 10 seconds, the thing moved 500 meters. You knew that from the last one. These are tied together. These are tied together. This equation gets stuck right here, and then you just carry through the integration and you get S. Now, the big key here is that these integral components are always, I mean, it doesn't matter whether it's this or anything else. This is the same thing as saying that S at 10 seconds. We found that out from back here. So you put both of these in here and you go through the integration. That's the toughest part, is to realize that the lower part and the upper part are connected to each other. And with that, once you master that, you've mastered all these problems. They all look about the same now. Now, he did throw you this one where, and I do these sometimes, but not that much. But okay, so here's your S, and you can list your V like this and your V of 50. So he lists his V this way. What does he do? He takes his V, sticks it right here, and then he takes the derivative of the V, sticks it right there, and he ends up with his acceleration. Now that he can go down here and put. Now, here's the thing. This is the acceleration with respect to S, not the acceleration with respect to T. So in other words, you may look at this plot and say, ooh, you had a jump in the acceleration. Maybe and maybe not. Depends on the circumstance here. Hang on. So you go back. Okay, so you already carried from 200 to 400. Take his derivative. He ended up with this. That's pretty much simple. And this one, the velocity doesn't change with position. Okay, that's the key. As opposed to our water going through here, our velocity did change with respect to position. If I look to the left, slower. Look to the right, it was faster. So that's pretty much those in a nutshell. And you'll see that it's basically the same type of problems over and over and over, just different drawings. Maybe it's going up, maybe it's flat, maybe it's going down, maybe it has a quadratic in it. So you got a quadratic. Well, you just take in this case, you differentiate it because you're moving from S. If you're given S, you're going to be moving to V, and then you're going to be moving to acceleration. Maybe. He may not ask you that. If you're given acceleration, you're going to be moving to velocity, then you're going to be moving to position. So here, you're taking a differential. Here, you're taking an integral. Okay, let's go in here. Okay, V with S. Well, if I've got V, okay, how do I get to the acceleration? I take a differential. How do I get to the position? I have to take an integral. So that's pretty much it. Okay, so here you have acceleration. You're moving acceleration to velocity to position. Then essentially you're going to take an acceleration, move it through an integral to get yourself to here and an integral to get yourself to there. Okay, so here you have a VS. Now, here's the thing about the VS diagrams. VS, just like this one, here it is. So in the VS diagram, what did we end up with? We ended up with the acceleration. Did we end up with the position? No, because the position sits over here. So we actually only have kind of one direction we can go here. Now, the other thing is you could have the acceleration with respect to position, and you could take that drawing back. Again, if you're doing that, okay, so here, maybe you have, let me go back to the problem. You've got two choices. You've got the velocity with respect to position, and you might have some curve, or you're given the acceleration with respect to position. Okay, let's look at the relationship. Okay, whoops, that didn't come out right. Acceleration is equal to v dv ds. Now, if I move it, if I just stare at that, and I say to myself, what is it that I'm doing? If I've been given velocity and I'm moving this way, I have to take a differential, because that's what's written right here. If, though, in fact, I have this, if I have the acceleration and I'm looking to get the velocity out of it, I got to go through an integral. And so that's something you have to think about. What were you giving? What were you given? And so let's look at what we were given. We were given the velocity as a function of position. So again, we look back, velocity of function position, we take a differential. Okay. So we take a differential of whatever that is. And so we have dv ds times v. Now, you'll want to do the graph here, and the graph is you need to think about each specific time and put this down. That'll give you the acceleration. Okay, so velocity, time. Okay, you're in the middle again. Moving to s, integrate, moving to acceleration, differentiate. Now, you know, of course, differentiates, just give me the slopes. Integral means what's the area under this thing? Okay, now he's getting into specifics in which he has better drawings. So he has a specific case where he has a drawing and he wants you to determine stuff. So here he's giving you the elevator starts from rest. Okay, so here's the thing. If it starts from rest, accelerates 5 feet per second. So here he's telling you, I want you to construct this thing. And then decelerates so he starts at 5, then he decelerates. Okay, 5 minus 2. You can accelerate, then decelerate. Determine the shortest time it takes to reach a floor 40 foot above ground. Okay, so wait a minute. So you're looking for this. That's his acceleration. So your thing is, you've got an acceleration. You're going to do a velocity. Then you're going to do a position. Whoops. And you want to basically look at that 40 foot above the ground thing. So it always starts from us, draw the 3 diagrams. Of course, this one, and this one. And based upon that, you can figure out information. Now, the key is you could accelerate for a few I don't want to say seconds, for a certain amount of time, and then decelerate such that you decelerated and you made that 40 foot above ground the shortest period of time. So I'll leave that one to you. I don't think I've assigned that one. So like I said, these have better accompanying drawings. But they all are similarly the same, essentially. There's a diagram, except the one where the elevator was, where you got to think a little bit. So there you go. There's your diagrams. And so we're reaching the point where if you look at the top right corner here, it says 9:45. I think I could fly through this curvilinear motion real quick. Let's go ahead and do it, because actually what you'll find out is nothing new. Okay, so you have a position. Okay, so here's a particle following a path. You've decided to put your origin right there. He doesn't say much about it, but there's going to be an x and a y. And as you look at this delta s, you can look at your velocity average. You can take, this is a vector and this is a vector, so you'll get these in vectors. How does the vector get represented? Well, previously it wasn't a vector, it was a scalar. Now it is a vector, and so as you go down, voila, something that's not anything new to you. If you track a particle through space, it's basically a Cartesian space is an x, y, z, and essentially you can write this. Now what happens here, and this is very important to take a look at in reference to the future, and that is, if I take a vector that is represented as xi plus yj plus zk, actually the differential operates on not just the x, but also the I, and not just the y, but also the j. But then what happens is you make this very important analysis that is right here, this paragraph that says that, hey, wait a minute, this doesn't change over time. Turns out that in polar coordinates, it does change. And then the polar coordinate is no longer I, it's represented as a UR vector, base vector, or U theta. Now, what is a base vector? It's I and j and k. It is a unit vector pointing in the direction. Here's your I, here's your j. A unit vector, a vector of length 1, pointing in the direction of the coordinate. It doesn't change, so therefore this comes out of it. Now, what happens to him is he's renaming this and renaming that and renaming this. So the time derivative of the position, which that's what that is, x dot is nothing more than this, sorry, dt, which then he decides, you know, instead of just calling it x dot everywhere, I'm going to rename it a velocity vector in the x direction, and that's what he's doing. Okay, so as you move along, you move to the acceleration, same thing happens. He's decided that, hey, instead of calling things this or this, I'm going to make a common symbol for each of those. AX acceleration in the x direction, AY is acceleration in the y, and AZ is acceleration in the z direction. And then, of course, if you want to know the magnitude of the acceleration, you take the square root of the squares. And so we've covered that. Essentially, we've got 1 minute left, and I think there's a delay in this, so that, okay, so if I look at the top right on my, oh, it's less than a minute. So as I look over here at the stream, picking up the stream at the same time, it's showing 9:49. So I'm about 10-15 seconds behind. And so I think we'll just call it good there. We'll come back, pick up right here on a motion of projectiles on Friday. I think that I'm going to do a live stream again on Friday, because I can make through the material much quicker, and I can start working problems and getting right to the meat of these issues and get ourselves underway. Okay, so with that, don't forget your homework. I think it's due on Sunday night. It's on units. If you have questions, send me an email with a specific question. I'll make a video on it. All right. Thank you. Okay, this is how you end the stream, and then we'll drop off from here.